All right. So here we go, part two, some gravity examples. So we've looked at this. We referred to this as the inverse square law, where the farther you get away from Earth, the less you feel the effect of gravity. So the gravitational pull is less. We call that weight. Here's the equation that describes force due to gravity in relation to the masses of the two objects that are attracting one another and the distance between their centers. Okay, so it's important to know that when you're standing on Earth, it's easy to think that the distance between you and Earth is zero. But again, we're talking about distances between centers of mass. So this is the radius of Earth, about 4,000 miles. So you're still this far away from the center of Earth when you're standing on the surface of Earth. Okay, and then again, g is 6.67 times 10 to the negative 11. All right, if we're looking at this chart, what we're considering here is, so this situation is you standing on the surface of Earth, all right? So Earth has a mass of big M, you have a mass of little m, and Earth has a radius of r. And so F, force, that would be your weight. And what's happening is we're changing, so Earth is staying the same and you're staying the same, but you're going out in space. And so if you're 2r away, it means you're an Earth radius away from the surface of Earth. So your weight would be 1/4 what it normally is. And so think about, excuse me, think about the fact that this is over an r squared, so when we square the radius, or when we double the radius, the square of that is 4, and so it's like dividing by 4, and so the force is multiplied by 1/4 or divided by 4. So your weight, the force due to gravity, would be 1/4 what it is on the surface. And if you were 2 Earth radii from the surface, meaning 3 from the center, the force you experience, your weight, would be 1/9 what it normally is. And then if you were to go on a diet and lose half your mass, the weight would be 1/2. Your weight would be 1/2. You're still on the surface of Earth. And then if everything were to change, so half mass, half of big mass, and twice as far away, so these two combined would provide 1/4 of the force. If you look at the equation up there, m times m, this would give us 1/4. And then the fact that it's double or twice as far away means that we would divide the force by 4. So it'd be 1/16 of the total. Okay, so this is more sort of conceptual. Sure, it's quantitative, but we're not dealing with the actual mass of Earth and stuff. We're just relating it to some original force or weight. What I'd like you to do is actually use your calculator. It's surprising how difficult it is to actually get these numbers correct when typing in your calculator. But basically, here's approximately Earth's mass. Let's say you or Joey has a mass of 70 kilograms. This is the distance from Earth's center. So here, Joey's standing on Earth. And if we plug this all into gmm over r squared, we get this, which is really close to what we get just from W equals mg. So 9.8, the acceleration due to gravity, comes from this number and the 6.67 times 10 to the negative 11. Earth's mass is, this is rounded, it's like 5.94 times 10 to the 24th or something like that. So if Joey were then on Mount Everest, so you would add this to get the distance from Earth's center. And if Joey were in low Earth orbit, so you would add this to get distance from center. See if you can plug those numbers in and actually get these numbers on the calculator. Okay, and so this isn't a formula that's given to you. This is something that, it's interesting to look at how the orbital period, the time it takes to go around, depends on how far away you are. So the farther you are, the more time it takes to go around. So first of all, sorry, I skipped ahead. For a satellite in orbit around Earth, the closer the satellite is to Earth, the less time it takes to orbit and the faster it goes. And the farther it is from Earth, the more time it takes to orbit and the slower it goes. All right. So the question asks us to derive an expression for the orbital period as a function of orbital radius. So the concept we're using is that gravity provides the centripetal force. That's all you really have to know, well, besides the formulas and some algebra. But this translated into formulas, so gravitational force provides a centripetal force. So this is like F equals ma, where this is centripetal acceleration, the v squared over r. So we're basically taking this formula, but we're not interested in the tangential or orbital speed as a function of radius, though you could look at that as radius increases, the velocity decreases. But what we're interested in is as something moves in a circular path, velocity or speed is distance per time, and the distance around a circle is 2 pi r, and the time around a circle we call t, the orbital period. So we're taking 2 pi r, we're substituting it in for v like this, and you should probably try this on your own, one, because it's totally fun, and two, it's good practice with your algebra skills. We're basically taking this expression and solving it for t, trying to get t all by itself. So you could pause and do that. Okay, you're back and you figured it out. So let's see, all this is squared, so we got 4 pi squared r squared over t squared. That's where this came from. Little m's cancel out. And here I have a complex fraction, meaning a fraction within a fraction, so I call this 1 over r. So I could multiply by the reciprocal. I'm sorry, that's not 1 over r, that's r over 1. So here's the multiplying by the reciprocal here. And then to get rid of the r squared in the denominator, I multiply both sides by r squared. That gets rid of that. This turns into just an r, which multiplied by this gives us the r cubed. And so we want this. So I think that I cross-multiplied. So the t squared goes up here, and then we would divide by the big G, big M, like this, and then take the square root. And voila. So this is a good thing to know, or a good thing to be able to figure out. So this is how the orbital period depends on how far away the satellite is from the planet or whatever it's orbiting that has that big mass. Okay, thanks for listening.